Welcome to lesson 2 in this series on metric and topological spaces. In this lesson, we're going to be looking at what are called indexed collections of sets and products of sets. As always, the booklet for you to follow along with and for the homework is in the description. Before we look at a formal definition, let's look at a couple of examples of indexed collections of subsets so we can kind of see what the end result will be. So, if U is a set, then we can have subsets called A1, A2, A3, and so on. And this little subscript is called the index. So let's look at some examples. If U is the set of natural numbers, and the set AI, which is the solutions to x squared equals I, where I equals 2, 4, 6, 8, so all the even numbers. Note that some of these sets might be empty, but that doesn't matter for our purposes right now. What matters is we can define a set for each of the even numbers that is defined by the rule we have there. Another example, if U is the set of real numbers, then AI could be the open interval from I to I plus 1. Or let U equal R squared, so this is just a 2D plane, and XY are coordinates in that 2D plane. And then the set here, now indexed by X prime, Y prime, so indexed by a coordinate. And each of these sets is the set of points such that they obey the equation of a circle of radius 1 with center X prime, Y prime. So the point of this last set is to say that the index doesn't actually just have to be 1, 2, 3, 4, so on. The index could be anything. So here, we're indexing by coordinates. Let's look at a formal definition of this now. So firstly, we have I, and this is the index set. This is the set where all the subscripts come from. And then the index collection of subsets can be written in this shorthand of A sub alpha, and then outside the curly brackets we'll say alpha in I. And these curly brackets are meant to be reminiscent of the fact that an index collection of subsets is in many ways a set of sets, and all the elements are labelled by alpha. Now we can use our set operations with this. So firstly, we have the union of all of these sets, and then very similar to when we write a sum or a product, we can write a little subscript alpha in I. So this means we're going to union over all the sets alpha in I. And then the union is defined as all the points in the universal set U that are also in A alpha for at least one of the alpha. Then secondly, we have the intersection, and then this is the set of points in U such that X is in A alpha for all of the sets in that index collection of subsets. There is something very specific about these definitions we'll get onto in a minute, but for now, just make a note of the fact that the set they're all a subset of, so U is implicit in the definition. And sometimes some books will call this the universal set. Note, we will often use the term collection or family whenever we're discussing sets of sets or indexed collections of sets, and we'll probably use the term collection or family interchangeably. So a quick example. Here, I is the index set that just contains the numbers 1, 2, 3, 4, 5, and AI is the closed interval from I to I plus 4. So part A, calculate the union of all of these, and part B, calculate the intersection of all of these. So for part A, we calculate the union, so it's the union of all the closed sets, 1 to 5, 2 to 6, all the way up to 5 to 9. And this is all the values all the way from 1 all the way up to 9. So it's just the closed interval 1 to 9. Okay, have a go at B on your own. Think about it, this is the closed interval, not the open interval. That's a bit of a hint. But have a go on your own, and then I'll put the solutions back up. Okay, now you've had a go. Here is the solution. You see that if you intersect all of these, the only point that's in all of the sets is just the point 5. So what if I is just the empty set? So this is where the maybe strange definition of the union and intersection is going to matter. So for the union, it's maybe what you would expect. If we union over all the sets indexed by elements of the empty set, the result is empty. However, for the intersection, so if we intersect over all the sets indexed by the empty set, we get U. We get the universal set. All of these sets were a subset of. Now this is maybe a bit odd. So let's have a think about why. So we said that the intersection was the set of all points x in U such that x is in alpha, is in A alpha for each alpha in I. So let's take an arbitrary x in U and let's see if it's in A alpha for every alpha in our index set. So, since there are no alpha in I, because I is the empty set, then there are no alpha to check. So we don't need to check if x is in any of the A sub alphas. So therefore, x is in A sub alpha for all of the alphas you consider. Because you consider none of them, x is in all of the ones you consider. And then this argument holds for every x we could have picked in U, and so therefore it holds generally for all of U. But there's a lesson to be learnt here. And that is, if there's nothing to check against, something is often true automatically. If it can never be wrong, it must be right. However, why does something like this not work for the union of the sets? Well, that's because in our definition of the union, we said there must be in at least one of them. And so it's that at least one that's doing the work for us here and stopping us have a strange result. Let's now look at how De Morgan's laws generalize to an indexed collection of subsets. So firstly, the first De Morgan's law generalizes as you might expect, where the union becomes an intersection, and similarly, the second law generalizes as you might expect. Now this might seem trivial, however I do want to issue a warning. These don't follow directly from De Morgan's laws in the last lesson. Those laws only held for 2 sets, not an infinite amount. Now this is true in general. We've seen several laws last lesson, and you'll come across them in different areas of maths, which are originally defined just for between 2 objects, and now that doesn't mean that it applies to an infinite amount of those objects. In order to see if it applies to an infinite amount of objects, will require a separate proof or a separate approach. However, the proof for these, or at least the proof for the first one is in the booklet, the proof for the second one will be an exercise. Okay, we're now going to look at proving some rules that at first glance might seem quite trivial, but the proof of them is actually quite tricky. So we want to prove that if you union A and B, and then take the union of all of those, it's equal to unioning all of the A's, unioning all of the B's, and then taking the union of that. So if we want to show that 2 sets are equal to each other, then the easiest thing to do, or a very common strategy at least, is to show that each is a subset of the other one. So we're going to break this proof into two halves, where we show the left-hand side is a subset of the right-hand side, and then we're going to show the right-hand side is a subset of the left-hand side. So firstly, let's take an arbitrary x in that set on the left-hand side. So we want to show it in that set on the right-hand side. So if x is in the union of all the A alphas, B alphas, then it must be in at least one of the A union B's. So it must be in A beta union B beta for at least one of the betas. Remember the union, remember a point is in the union if it's in at least one of the things we're unioning together. So if it's in at least one of them, this means it must be in at least one of the A betas or B betas. And if it's in at least one of them, this means it's either in the union of all the A's or it's in the union of all the B's. So if it's in at least one of the A's or one of the B's, then it must be in one of these unions. And therefore x is in the union of all the A's, the union of all the B's. That's quite a mouthful to say, to be honest. But because x is in this, the left-hand side is a subset of the right-hand side. Okay, so let's do the second half of this proof. So let's take an x from the left-hand side. This x must be in either the union of all the A's or the union of all the B's. And therefore, x must be in one of the A sub betas or one of the B sub betas for at least one of the betas in our index. And therefore, it must be in A union B for at least one of the betas. And therefore, it's in the right-hand side. So here we've shown the left-hand side is a subset of the right-hand side. And because both sides of this equation are subsets of each other, we showed in last lesson that they must be equal. Okay, have a go at the next example. The proof follows a very similar structure, but justifying some of the intermediary steps is still quite tricky. So maybe if you have separate paper, I'd recommend using that rather than the booklet, because it is quite tricky. But once you've had a go, come back to the video and I'll put the solutions up. Okay, now you have a go. Here is the proof. And I understand if you need to pause the video and really read through it and think about it. These proofs are not easy. We're now going to move on and look at products of sets. So if big A and big B are sets, the product, A cross B, is the set that has the elements little a, little b, where little a is in big A and little b is in big B. We can rewrite this, or we can write this formally as A cross B is the set AB that obeys the rule little a is in big A and little b is in big B. And this is an ordered pair, so AB is not equal to BA. And this means, in general, A cross B is not equal to B cross A. So now let's look at some examples. So first, our first example is R squared. Now R squared is just the 2D plane, and as a set we can think of this as R cross R. And this is the set that consists of all coordinates x, y, such that x is in R, y is in R. Our second example, A is just 1, 2, 3, and B is just AB. Then you can work out A cross B on your own and work out all the elements, or I'll just put up the answer in a second. Okay, either you've had a go or you just want to see the answer. So the set A cross B consists of all of these elements. And this is why this looks a bit like multiplication. If you look, A has 3 elements, B has 2 elements, so A cross B has 6 elements. We can generalize this product to include more than 2 sets. So if A sub I is a countable or finite collection of sets, then we can define the product with this capital pi, and this is just a product of all the sets in that collection, and then this contains all the elements of the form A1, A2, and so on, and then the number of elements in those brackets is just the same as the number of sets in our collection that we're producting together. So let A, B, C be sets, and we're going to prove that A cross B intersect C is equal to A cross B intersect A cross C. So firstly, A cross B intersect C is the set of points xy such that x is in A and y is in B intersect C. Therefore, if y is in B intersect C, y is in B and y is in C. So this means xy is in A cross B and xy is in A cross C, but that there is just a definition of the right hand side. Okay, have a go at the next one in your booklet and then come back to the video and I'll put up the solutions. Okay, now you've had a go. That's all for this lesson, and it is obviously useful to go through the homework problems and go over the definitions before the next lesson.